my name is Callie Chappelle, and thanks for tuning into this video about currents in the magnetic field, a couple of more complicated cases. This video is the subsequent video to the previous one about the Biot Savart law. I wanted to keep that video a little bit shorter and not go into these two detailed cases, or actually three detailed cases, which are a little bit more complicated than the two that we talked about in that video. So the first thing that we wanted to talk about was what happens when you have two wires and what is the force between them. Okay, so force. Whatever. I'm just gonna type this because I think it looks better. I know I'm really into the aesthetics. All right. Force between two wires. So let's say that we have two wires and they are parallel to one another. So let's draw them here. So here we have wire A and here we have wire B. So let's label them so I don't forget what's A and what's B. Okay, so here is wire A and here is wire B, and we have current flowing in the same direction through both A and B. So we also need to define a couple of variables. So I'm going to call this distance between wire A and B distance D. And I'm going to call the length of wire B LB. And this length is contingent on the fact of how much of wire A is actually exerting a force on wire B. So let's say that wire A goes off for a little bit and then bends here. Well, the distance of LB would just be the section of wire A that is parallel to wire B, or the section of A that has a magnetic field that is that results in a force on B. So parts of wire A that do not exert a force on B are not relevant, or the parts of wire B that do not exert a force on A are also not relevant. So let's define a couple more things. So we're going to go through how we figure this out in a second, but I'm also just going to note right here that the force or the magnetic field due to A at wire B is pointing down, and we can figure that out by using the thumb straight curve rule by sticking my thumb in the direction of wire A and curling my fingers in the direction of the magnetic field. And by doing that, you'll see that the field at B is downward. I'm just going to draw a picture of this because sometimes it's hard to imagine this. So if my thumb is going this way, so that's the same as that's IA, and I'm curling my fingers around. How do I want to do this? Yeah. I'm curling my fingers around. It's going to be something like this, where my hand, let's try to get a little perspective, is going like this. So it's curling around, down, and back up again like this. So this is BA. Okay, and that's why when you're down here, my fingers are starting to curl down, and then they're going to come back up. Okay, so even though this picture is not great, try just curling your hands, and you'll see that at wire B, the magnetic field due to A is pointing down indeed. And then the force due to on B due to A is in this direction. Force on B due to A is in this direction, and we can do that by utilizing our favorite equation, F equals IL cross B. If L is going this direction and B is going down, well, I use the regular right-hand rule to figure this out. So I cross B, force is going to the left. And what am I doing? I'm using my hand to show I, so like that, if this is the back of my hand. Okay, so my fingers are pointing in the direction of I, or in this case actually the length vector, and then B is pointing down, so then I flip my fingers down. Let me see if I can just show my fingers going down now. I cross B, you'll see that my thumb here, which is the direction of the force of A on B, is here pointing in this direction. So that's how we figure that out. Now let's look at the magnitude, okay? So the magnitude, as I said right here, magnitude is our lovely friend, this cross product, force of B on A equals the current in B times the length of B, that's just the length of B that is actually being affected by A, and then the magnetic field at B due to A. Okay, so again, this is the length of wire B affected, and I have to be careful because I don't want that to be confused with the B field. And then this is the magnetic field of A at B, at wire B. And this can be rewritten as IB LB times mu naught IA over 2 pi d. And this is just the magnetic field at of A at B. And this is from the Biot Savart law. So if you're curious about where this comes from or want to learn more about it, then watch that previous video about Biot Savart. And direction, so direction, we figured out by using those two right-hand rules. Remember, first we figured out the direction of B, right? Because we need to know this. This was already given to us, but we need to figure this out by using the thumb straight curve rule. And then we wanted to figure out the direction of the force, and that we used the normal right-hand rule for. So that was what we did here and here. We could also use a trick, and that is if you have two parallel wires, if the current is flowing in opposite directions. So examples of opposite directions, just so you can have this in your mind, is if you have one current going out of the page and one current going into the page, or let's say you have two wires and one eye is going this way and one eye is going that way. Contrary to what you'd expect, these actually repel. So the force between these two wires would be this direction, would be this direction, and this direction, and the force between these would be these two directions. And then if I, in the same direction, they will, you guessed it, attract. And I like to remember this is, if I am with someone who's very different than me, I will repel them. And if I'm in someone who's going the same direction as me, I will attract them. Okay, and that's different than with things like electric charges, where it's like you're talking about the electric field, that's E. This is like I, like very personal. So again, if you have two wires and the current is going in the same direction, these will attract. And then similarly, if you have eyes going this way here and eyes going this way here, these will also attract, and that is what we just saw here. These two wires, the currents were going in the same direction, and the force between them was attractive. Cool. The next thing that I wanted to talk about was the force due to a current loop, and this is a little bit more conceptual, but I think it's pretty cool. And actually, what the end result of this that's really cool is a current loop actually looks just like a magnet, a bar magnet. So field due to a current loop, or a loop of current. Let's make that all one line. So, like I said, a current loop is just like a bar magnet with a north and south side, and this actually helps explain why magnets are always dipoles, because if you slice a loop in half, you'll get two loops with two sides. But let's start quickly by just looking at what a loop of current would look like. And in actuality, this would be something like a semi-loop, not a full loop, that's connected to some kind of battery. So perhaps it would look something like this, where you have a loop, and this is connected to some kind of device that has a battery that produces a current that goes around the loop like this. But for the sake of simplicity, let's just approximate this. Let's approximate it by simply drawing a circle. And I'm going to make the circle kind of fat, because this is going to represent a wire. Okay, so here's our loop. And around our loop, we have a current. And let's say that the current is flowing, I don't know, what the heck. Let's say the current is flowing this way. So let's figure out what the magnetic field looks like around this loop of current. So we know that we can utilize the thumb straight curve rule to figure out the direction of the current at any particular point. So let's start here. Let's say we want to figure out what does the magnetic field look like around this point. So I'm going to point my thumb in the direction of the current, which in this case is into the page, and I'm going to curl my fingers around. And remember, we know that around a wire, magnetic fields form circles, so it's going to form a circle. Wow, that's a really terrible circle. That's so bad that I think I'm going to redraw it because I'm a little bit embarrassed. That came from my hands. This one's not that much better, but slightly better. It's going to be curving. See, that gave you a lot of time to actually do the right-hand rule, right, while I'm chatting away. A magnetic field that goes like this. So big thing that the big takeaway here you want to get is here at the center, the direction of the B field is up. Well, I don't know why this is so thick. I'm going to make this a little bit thinner. So let's do the same thing here. So here we want to figure out, we're going to put so I is going this direction, so I'm going to put my thumb in that direction, and I'm going to move my hands around and see what is the direction of the magnetic field at this point. Well, if you went like that, you'd be right. You'd be right. So it's going like that, and again, on the inside of this loop, the B field, even at this point, is also pointing up, and this is on the inside, please note, okay? So let's do this one more time. You probably sing along if you know the lyrics, because I'm sure you're going to guess what's going to happen. Okay, so direction of current is now here out at me. So what is the direction of the magnetic field at this point? You guessed it. It goes like this. And again, on the inside, you'll see that the magnetic field is pointing up. So this explains, and not only is on the inside, or not really on the inside, but like on the top side of this loop, the magnetic field is pointing up. On the bottom side of the loop, the magnetic field is also pointing up, but it's pointing into the loop, okay? Okay, so here is like this. Well, does that look at all like a bar magnet? Why, yes, gee, golly gee, Callie, it kind of does. So let's say that we have a bar magnet right here. And this bar magnet has, I think you're going to see, you're going to see where I'm going with this. It's not doing what I want it to do. This bar magnet has I'm just going to make this so obvious to you. The north side and a south side. And on the north side, we know the magnetic field originates on the north side and comes down here. Wow, okay, that was really bad. Pretend like you didn't see that. It comes down here to the south side. Originates from the north side, comes down here to the south side. Wait a minute. This looks just like what's happening here with the B field, right here with this loop of current. Well, indeed, you would be right. This is exactly, it's pretty cool that a loop of current actually functions the exact same way as a bar magnet, with a north side, and also a south side. So, you may think back to when you're first learning about magnets, and you're probably like, well, when I learned about the electric field, we just talked about monopoles. Why do we have all this dipole business? And your teacher probably told you that it's because you can only, as far as we know, have magnetic dipoles. And the reason is, if you have a loop of current and you slice the loop in half, you're still going to have one side and one side. You're always going to have a north and south side. So, for example, if we have a loop of current like this, let's make this a pretty fat loop of current, okay? It's pretty fat. So it's like that. So here's like the back side of it. And let's say that we sliced it in half, okay? We sliced it in half just like this, and it's not a Mobius strip. Don't give me that crap. I know all you smart Alex are out there. So we slice it in half with scissors. Those are my scissors. Well, what do we get? Well, we get two smaller strips. We get two smaller strips. Like that. There's one. Here's the other one. And this big strip, this had a north side and a south side, and then when you cut it in half, you still get a north side and a south side, a north side and a south side. And the north side being, if this was not a strip, but it was instead just a flat disc, on one side of the disc would be the north side, and on the other side of the disc would be the south side. I'm not talking about like if you cut it in half with this side. It's if you had this area, if you had this like a flat thing as a disc, what side of the disc it would be on. And you'd always have a north and south side. Similarly, just like we know, if you have a bar magnet with a north and south side, and you cut that magnet in half into two pieces, well, that's why you end up getting a north and south side again. Okay, it's the same thing with a loop of current. So that's pretty cool. The last thing that I want to talk about, and I'm not going to go into the theory so much about this, but just some equations that you should know are coils and solenoids. And a solenoid is just essentially just a really long coil. So the last thing I wanted to do is just give you some equations and then tell you what all of the variables mean so you can apply this in cases of a coil. Now, really quick, conceptually what's going on is if we have a coil, so there's my coil, a terrible coil as usual, and we have current flowing through it this way. So here we have our current, I'm just going to draw it here on the side, but it's flowing continuously throughout this coil. These coils, which are just many loops of current, like we can see here that a current loop produces a uniform magnetic field in the middle. Well, all of these are going to still point in the same direction, so it creates a really, really uniform magnetic field here. And I'm just going to label this B inside of the coil, and that warrants a special equation that is the magnetic field inside a coil is mu naught n, which is the number of turns. So if we were looking at this would have 1, 2, 3 turns, times r squared. R squared represents the radius of the coil. R squared times I, which is the current in the coil, times 2, times the quantity of r squared, again that's the radius of the coil, plus z squared, so that's the distance between some point. So like let's say we wanted to know what is the magnetic field here, it's the distance between the center of the coil and that point, z squared to the 3 halves. Okay, and then also, let's say that we weren't curious at some point z, we just wanted to know what the magnetic field is in the middle of the coil, which is generally what we want to know. So we'll be coil, then would be, we would not have this z term, so it's just mu naught n r squared I over 2r squared. If you are really struggling for some real estate, if you have a note card in your exam or your quiz, then I would just put this one and know that when we're asked about at r, this z term just goes to 0. The second thing is a solenoid, which as I said before, is just a really long coil, and that equation is B solenoid. I always like to label these, have like excessive labeling on my note card or when I'm taking notes because I never remember in which cases you can use various equations, is mu naught n, again, which is the number of turns, over L, which is the length of the solenoid, times I, which is the current in the solenoid. So hopefully this video was helpful for you, and hopefully I will see you in future videos. Good luck.